Okay then, we shall start session 4. Just give me a minute. Yeah, it should be good. Okay then, so just a second. So, good evening everyone. This is Mustaq, and this is fourth session for the Nanomaterials course. And so, let's move. So I'll just briefly go on what sir has discussed in previous week and also this week. So yeah, so this is mole fraction of vacancies that are depending upon the curvature, how the mole fraction of vacancies changes. For example, you can have convex curve, or you can have concave curve. So depending upon the curves, how the mole fraction of vacancies or the vacancies that are present inside on the surface of the body will change. Okay, so for example, if I take here, let's say we have a concave surface like this, and we have a convex surface like this. So how we are going to say that which surface has a more number of vacancies? Like we can have more number of vacancies in concave, or we can have more number of vacancies in convex. So how exactly we define, and what is the relation between the mole fraction of vacancies and the curvature? So let's go with the free energy. We know that delta G is equal to, let's say, just a second. Okay, so delta G is equal to delta G total is equal to delta G. Sorry. Yeah. So delta G on bulk plus delta G, or the excess free energy that is coming from the surface. So there is a total free energy, and let's keep delta G total is equal to, what is delta G bulk? Let's keep that it is already delta G bulk. Then what happens? Delta G bulk plus, what is the excess free energy? Excess is the free energy that is arising from like surface. So if I define it like just like I defined in previous classes, well, delta G for surface will be volume of the atomic volume, or the volume of the single atom, multiplied by surface energy as surface divided by K. Second. Just a minute. So and okay, just give me some. Yeah. Start. So let's back to the explanation. For example, this is my convex and this is my concave. Something I'm missing here. Just a second. If I have this as a convex, sorry, there is a convex and this is a concave, and we can write it as delta G is equal to delta G total is equal to delta G bulk plus delta G excess free energy. That's the equation. So for excess energy term, we define like delta G excess is equal to atomic volume omega multiplied by surface energy divided by radius. To surface energy, like surface between two surfaces, or surface between surface and vapor, or surface between gas. So like this, yeah. Surface and S1 and S2, like there are two surfaces. So then the next step will be how to find the mole fraction. To find the mole fraction, or we can find the fraction of vacancies. Like the fraction will be defined as number of vacancies divided by the number of atoms. So if I define it like that, so this will be my mole fraction of vacancies, that is equal to exponential minus delta G by kT, where delta G is the free energy, or you can say delta G is delta G total. And delta G total is your free energy divided by K. K is your Boltzmann constant and T is absolute temperature. So let's go to the next slide. Now we know what is the relation. So once you know the relation, you can define it as mole fraction of vacancies is equal to mole fraction of vacancies is equal to XV is equal to exponential is equal to exponential minus delta G total divided by kT. So this is a relation. Now we know what is delta G total. So sorry, just a second. Yeah. So we know from our relation delta G total equals to delta G total equals to delta G bulk plus this excess free energy. Then the delta G bulk we'll remind it, the delta G bulk will remain as delta G. Then we have delta G excess will be substituted here as omega surface energy by R. So XV is equal to exponential of minus delta GB into gamma by R, and that it is, and XV is equal to we can approximate exponentials as exponential of x exponential of x is approximately equals to 1 minus x. So if you define it like that, then it will be 1 minus or equals to KT. So this is our relation. So if we have a convex surface, for example, which has a convex surface like this, where it has a positive curvature, so R is positive, then XB will have a value. So for negative curvature, for example, for concave curvature, the R is negative. So it will turn out to be like, yeah, that will be 1 plus K T into R. So this is how it turns out to be. Into some constant term, or we can add C2. Yeah. This is what happens. So here you can see, so this is your convex surface, this is your concave surface. So what happens, the mass transport happens like this. So the atoms will join, the atoms will come from here to here. What about the vacancies? Vacancies goes from here to here, because that's how the substitutional diffusion happens. For the substitutional diffusion, you need to have the vacancy movement, or for the movement of atoms in substitutional atomic diffusion, there is a need for the vacancies, because the atoms can't jump and jump without the vacancy. So if we have a movement of atoms in one side, then we have vacancies movement in the other side. So if I define here, it will look like, suppose this is your atomic mobility, and this will be your what do we say, the vacancies mobility. Yeah, so this is how it happens. And so even if you once we prepare the nanoparticles, and we keep it in a nominal temperature, then the atoms start diffusing, and to minimize the surface to minimize the surface energy. So the atoms are diffusing from like the concave surfaces to convex surfaces, and totally we have a bonding. So we need to study the properties, so that these nanoparticles doesn't agglomerate or have a bonding like the sintering of powder particles. Now let's move on to this other topic. So yeah, after that we have discussed how the lattice parameter, or the lattice parameter of any nanoparticle depends upon its size. So for example, if we have, let's say, for example, if I have a lattice parameter, for example, if I have a nanoparticle, sorry, nanoparticle like this. Suppose this is my nanoparticle, and inside I have many number of atoms. Like this. So how the lattice parameter is going to change? So for that, we first need to define what is the excess energy. Now let's start. Let's add some more slides. Yeah, sweet. Recording. Great. Yeah, so so if this is my particle diameter, sorry, if I have a nanometer, so I have a, if I have a nanoparticle like this, and it has many number of atoms, so how the lattice parameter is going to change? So for that, first we need to define the surface tension, or the excess pressure that is on the nanoparticle. So if I take this surface, so this is my surface, and this is my the outer environment and it is the bulk environment. So there is a difference in pressure, and that difference in pressure is defined as delta P. And suppose if I take like this, and this will be my theta value, and here I have the surface tension, this side I have a surface tension. I'm just defining for a liquid film. If I have a surface tension, then this direction or its mutuals, here we have theta, so it will become this will become t cos theta, and this side will become t sin theta. So the horizontal components will balance out from this side 1, from side 1 and side 2, and the first side, the horizontal component t cos theta, and second side will have a horizontal component of t cos theta, so they both cancel out, and we have only vertical components, and the vertical components are 2t sin theta equal 2t sin theta, and divided by, because it is a surface tension we defined as a force per unit length. So if we want to dimensionalize it equals to delta P, we divide it by this arc length, that is for example I define it as a dl equals to, and what is delta P, which is the excess pressure. So far so good. And if I write that equation again, which is delta P equals to 2 delta P equals to delta P equals to 2t equals to 2t sin theta. Sorry, just a minute. And again derive it. So just for a second. Yes. Inside the surface. If this is my theta, and here I have t, here I have t. And if I closely watch this one, it will become t. Here we have theta. So the vertical component is t sin theta. The horizontal component is t cos theta. We have 1, we have 2. So from 1 and 2, the horizontal components will cancel out, and the vertical components will add up, will give to 2 sin theta. Let's go to the next slide. So if you want to dimensionalize with delta P, as I said before, which I can write delta P as 2t sin theta, because the surface tension unit is force per unit length. So to dimensionalize with the delta P or change in pressure, we have to divide it by length, and that length will be given by the arc length, which is dl. So if you are talking about the small angle approximations, in which the sin theta will be approximately equals to theta, and so theta and approximately is equals to tan theta. We want to represent, I'm just representing to let you know the math. So theta will be theta will be equals to, you can represent theta as, you can represent theta as arc length divided by radius. I will represent the diagram here. This is my thing. So this is my curvature. So if you want to measure the excess pressure delta P, this is my T, this is my T. Here is the horizontal component, which is T cos theta, and vertical component T sin theta. this is my arc length. Yeah. So far so good. Or I can represent a dl by 2. So I'll change the case. So if I substitute in delta p equation, that will be 2t theta will be dl by r divided by r, and that delta p will be divided by dl, right? Yeah, it should be dl. If this dl gets cancelled, that will be 2t by r. That is excess pressure. So if I put my excess pressure is equal to 2t by r, sorry, 2t not, it should be 2t, it should be, it should be 2. Yeah, if I take for solids, the surface tension is equal to surface energy, so it's not surface energy. So that will be equals to 2. So for liquids, for surface tension is equal to surface energy, and if we just substitute, if we take it as if we assume the surface energy remains constant, then we can substitute surface energy there. So the next term will be now. So the next term for the derivation of that equation will be the compression factor. So the compression factor K. So it is the compression factor. The compression factor is equal to 1 by V naught dou P divided by dou. This is our compression factor. So you know the volume of a cube. Volume of a cube is a cube. So this will turn out to be, if we do delta V in terms of change in volume, then it will become 3a square and delta A. Yeah. So then K equals to 1 by V naught into, what is the change in pressure? Change in pressure is 2 gamma by R, and delta V is 3a square delta A. So if I divide as V naught, then if I substitute these terms, then it will become K equals to 1 by a cube multiplied by 2 divided by surface energy divided by I just made a mistake. Let me write it. So this will turn out to be a cube divided by 3a square delta A. So this one gets cancelled, and we have so delta A by A equals to 2 gamma divided by R into K. So this is how it depends. So if I write it in terms of like 3, right? There is a 3. Yeah, there is a 3, extra 3. So yeah, this I think, yeah, this is how it gets, and yeah, delta A by A is proportional to surface energy divided by R, or diameter, or the size of the nanoparticle. So the change in lattice parameter, or the lattice parameter depends upon the surface energy and inversely proportional to the R. So if the R um, terms decreases, then this will increase. So there is change in lattice parameter. This will be A naught. A naught. Yeah. This is A naught. Oh, sorry, yeah. So that is A naught. So the decrease in size will also affect the delta A, and also if there is a change in surface energy, that will again affect the change in lattice parameter. So this is the relation. This is how we arrive. Oh, sorry, there must be like 3 shouldn't come here. It's just yeah. I guess. Sorry, here it will become 40 by R, right? Yeah, it should become 40 by R. So the finally this will turn out to be 4. Let me change. This is 4. This is 4. Yeah. Okay. So let's move on to this. So this is how we arrive. So increase in particle diameter. See, if we increase the particle diameter, the lattice parameter, the lattice parameter will go towards the bulk lattice parameter. See, so this is how the particle diameter changes. If we decrease the particle diameter, the lattice parameter also decreases. So from this relation we can see, and how it also depends on the surface energy. So decreasing the particle diameter will increase the surface energy, in terms decrease the lattice parameter. So please remember, we are treating it as change in lattice parameter, not the direct lattice parameter. So in change, for example, if we have a naught, and if some value increases, then that A naught minus the next term. So the next term must decrease. That's why we have a decrease in lattice parameter. We have a decrease in lattice parameter. Okay, so this is how the relation and this the theoretical or empirical values are defined, and this is like, these are the experimental values. Okay, then let's move on to the next slide. So yeah, so other thing we have, sir had described what is the magic number. Now let's define. Other term that was defined was the magic numbers. So how do you define the magic numbers? So what are magic numbers? So let me give an example. Suppose what is happening from this size, for example, these are the nanoparticles. So this is the increase in size of the nanoparticles. So at first we have 13 atoms, then we have 55, then we have 47, 147, then we have 309 and 561. 561 nanoparticles. So what is happening? So why we call these numbers as a magic numbers? So magic numbers are nothing but when there is a phase transformation, or when the nanoparticle size is increasing. So we can't just accommodate any atoms into the nanoparticle. So to stabilize its energy, or we can say the total energy of the nanoparticle. To stabilize the total energy of nanoparticle, the nanoparticle tries to accommodate only certain number of atoms, and those certain number of atoms have a certain number, and this number is called as a magic number. So for example, so far we have discussed the perfect sphere, but to retain the physical nature, to retain the physical nature of the crystal structure like FCC, BCC, to retain these crystal structures, the spherical shape gets distorted. Now how it gets distorted? Because of the surface energy, and because of the nanoparticle have different facets, like it has one side, it has a 111 plane, one side it has a 100 plane, and that's why the nanoparticle tries to accommodate only certain number of atoms. and this number is called as a magic number. So yeah, you can see from first one here. At first we have 13 number of atoms. Now again, how this 13 comes from? So if we see the stacking sequence of FCC, we have the stacking sequence of FCC is ABC type. So how the ABC type look like? So for example, if I take an atom here, 2, 3, 4, 5, 6. Suppose if this is our B layer, then what about the A layer or the top layer? Top layer will come like this. And about the bottom layer will be like this. Yeah. So if this is A, this is B, this is C. And if the A sequence is repeated after B, it will be AB, that is a hexagonal close packed structure. But if we have a ABC type, then it will become FCC. So if we take the middle atom like this one, so to totally hide this middle atom or to totally cover this middle atom, how many atoms are required? So if we consider only B layer, we have 1, 2, 3, 4, 5, 6. We have 6 atoms. And if we consider only A layer, we have 1, 2, 3, 3 atoms. And we have, if we consider C layer, we have 1, 2, 3, 3 atoms. So the total number of atoms will be 6 plus 3 plus 3, that is 12. And the middle atom will be, or the atom that we are trying to cover, will be 1. So we have 13. We have the first magic number. So this is how it happens. So once we start putting the sequence, if we add another sequence, then the number of atoms that are accommodated will be 55. And if we move on, if we add some more layers, then the nanoparticle will try to have 147 number of atoms. And if we try to add even more number of layers, so the nanoparticle again will accommodate the 309 number of atoms, and so on and so forth. So this is how the sequence for the formation of an FCC structure happens. So we even have its name like octahedron. So let's move on. So see, here they have given like 92, 76, 63, 52, 45. That is the surface percentage or the number of atoms that are present on the surface. And we can even define, or we can have a relation, or we can have an empirical relation. So let me give an empirical relation. Yeah. Let's do this. So if we move on to the empirical relation, and suppose if this is a nanoparticle and it is accommodated with atoms, let's consider the atoms as the hard spheres, and this one has a size R0. R0, and the atomic radius can be taken as RA. Then the R0, which will be 4 by 3 pi R cube, R0 cube, equals to, and the number of atoms that can be accommodated, which will be Na, and volume of the each atom will be 4 by 3 pi Ra cube. So 4 by 3, 4 by 3 pi gets cancelled. Then what do we remind? That is R0 equals to Na of 1 by 3 times Ra. This is our first relation. Now let's move on to number of atoms that are present on the surface. That will be given as capital Na equals to so the surface of this nanoparticle, that will be equals to 4 pi R0 square divided by the surface area of each atom, 4 pi Ra square. This will be equal to 4 pi gets cancelled. Then R0 square will be Na 2 by 3 itself, fraction of surface atoms will be Na 2 by 3. So if we consider, so these are, there are many assumptions here. So first we consider the nanomaterial, the nanoparticle as a perfect sphere, and the atom is also a perfect sphere, and also it's like we are not considering the surface, the volume that is remained when you are filling with spheres. There is an extra volume that we call as a void when the atoms start to get like arranged in a given sequence. So this is the fraction of atoms or the number of atoms. So if we define it, or if we want to define it, so if we define it like this, and the fraction F will be number of atoms on the surface divided by total number of atoms. So that will be equals to Na equals to 2 by 3 divided by Na. So Nf will be equals to Na 2 by 3 minus 1. So N fraction will be Na power 1 by 3. So this is our relation. So this is how we can in a fraction. So this is how we define the fraction of atoms that are on the surface. And if we multiply this NF into 100, that will give us the fraction of atoms. Oh, sorry, the percentage of atoms. Right? Yeah. So it should be percentage of atoms on the surface. Now let's move on to how the so far we have discussed how the lattice parameters. See, let's go backwards. See, yeah. At first we have discussed how the mole fraction of vacancies change with the surface or with the curvature, and the next we defined how the lattice parameter gets affected with respect to surface energy and the particle diameter. So again we have the magic numbers, how the surface energy affects the number of atoms that can be accommodated in nanoparticle. So let's move on to how do you find the surface energy? So yeah. So how do you define this? Just give a second. I'll add more slides. This will do. So at first we have, so for example, let's move on to the next slide. I will show you what happens. So for example, if I have a 100 surface, so if I take the simple cubic, for example, this is 100 surface. So if I draw a simple cubic, it will look like this. We have each atom at the corners. So then what is the coordination number? The coordination number is 8. That is represented as Z. So each atom is covered by 8 atoms. So if you consider this atom, it is near to this one, and the atom which is and the next unit cell, and the unit cell um, in front of the screen. So we have 1, 2, 3, 4, and one is on the top, 5. So we have 1, 2, 3, 4, 5. Suppose if I count it, it will be like 1, 2, 3, 4, 5. So it will become 6. It will become 6. Yeah, it should be. Just give me a second. Coordination. So that will be 6. Sorry, it's not 8, it is 6. So we have one atom here, one. So we have 1, 2, 3. So another 3 will come from other lattices, from left one, top one, in front of the screen. So we have the coordination number as 6. So what I'm going to do is I'm going to cut along this surface 1, 0, 0. I'm going to cut this crystal along 1, 0, 0 direction. So what happens? So once the crystal cut, now how many atomic bonds are lost? So the atomic bonds that are lost is given by the coordination number. Sorry, the atomic bonds that are lost should be given by, just a second, should be given like this. It should be given like should be given by the number of bonds that are broken. So if we cut the surface like this, then what happens? So on the surface we have 4 atoms, like 1, 2, 3, 4, and below there is a 1. So we have one atomic bond that is missing. So 1 multiplied by the bond energy. So if we are considering 2 atoms, so the bond is formed between 2 atoms. If we consider only 1 atom, and that 1 atom, the bond energy will be bond energy divided by 2. So this is the excess energy. So for example, now the energy required to sublimate a simple cubic, that will be given as sublimation equals to, what is its coordination number? Coordination number is 6 multiplied by the bond energy divided by 2. For example, if for any crystal structure if we take, then this coordination number will be written as Z. So that E, excess energy, will turn out to be 1 into sublimation divided by Z. And for simple cubic, the coordination number is 6. Just a second. Yeah, the coordination will turn out to be 6. So yeah. So then the excess energy, or it can be represented as surface strain energy of 1, 0, 0 will be Ls divided by 6. Or we can even represent in this term, in bond energy term, that will be bond energy divided by 2, because only one bond is broken. And so far I have assumed that I am perfectly cutting, my cut is parallel to 100 plane. Now what happens if 100 plane is like tilted towards some axis, or the cut is not exactly parallel to 100 plane. So what happens? So here you can see, this is our scenario. Our 100 plane is this. Sorry. That our 100, yeah, our 100 of simple cubic is this, but our cut is with respect to 100, but not perfectly flat or not perfectly parallel, but it is inclined to a certain degree, and that is given as theta. So what happens now? So once we have a cut not parallel to 100 plane, the whole scenario or the mathematics we have assumed will be changed. So even though we can simplify it, for example, to solve the complex mathematical models or mathematical equations, we non-dimensionalize terms. So the same thing I'm going to do is the most important term that we are going to use here is the length term. So what I'm going to do is I will non-dimensionalize the length term. So I'm going to take like unit length. So and if I write the triangle, if this is my cut surface, this is my cut surface. And this is my theta. And what happens? This is my theta. Then if I'm assuming this as my unit length, and so the number of bonds broken. So if I resolve this unit length into the x-axis, if this is my x-axis and this is my y-axis, if I try to resolve this into two axes, then this unit length will become the x term will be cos theta multiplied by 1. Here is this. So x will be cos theta multiplied by 1. What about y? Y will become sin theta multiplied by 1. So x is cos theta and y is sin theta. And put it on the next slide. So let me draw that diagram again. This is my x, this is my y, this is theta. So x will be cos theta times 1, that will become cos theta, and y is sin theta times 1. It will become sin theta. So the number of broken bonds along x will be xn will be cos theta by a. Number of broken bonds along y will be sin theta by a. Sin theta by a. So these are the equations for number of broken bonds along x and number of broken bonds along y. So far we have represented in terms of like 2 dimension. Now if we go into 3 dimension or into the screen, if I take this as z axis, if I take into the screen, then so into the screen also we are considering unit length. So into the screen Zn. Okay. So Zn will be unit length divided by A. Now, if you are considering surface energy is represented in terms of surface number of surface energy per unit area. So we have to represent it in terms of area, the energy per unit area. So if you consider area, then this xn times zn will be equal to cos theta times a square. And what about yn? So yn zn term will become sin theta by a square. So the total number of broken bonds along the x-axis, along the y-axis, along the x and xz axis, and xz plane, and along the yz plane. So the total number of bonds n. So the total number of bonds broken n equals to just give me a minute. The number of bonds that are broken will be given by n equals to, along the xz and yz axis, will be equals to 1 by a square cos theta plus sin theta times the bond energy, that will be bond energy divided by 2, and this can be represented as bond energy divided by 2a square cos theta plus sin theta. Right? Go back. Yeah, perfect. So this is how we get. And if we give, like, this is the number of bonds broken, and if I write like this is the surface energy, excess energy we can call it. So that surface energy can be represented as the bond energy divided by 2a square into cos theta plus sin theta, and this modulus term represents the value of theta that we are going to insert. So for example, if I have, if theta varies from theta, so if theta varies from 0 to 90 degrees, so then sine will be positive. If theta values from 0 to 180, then sin theta will be negative. And why we are considering the modulus term? The modulus term arises because sine of minus theta is minus sin theta. So that's the only reason we are maintaining the positive sign. So to maintain the positive sign, we are going to insert the modulus term. So clearly theta, and so yeah, and depending upon the angle, so for example, if I write totality, then it is 270. Here tan and cot are positive except sine, so again sine is negative, but between 270 and 360 the sine is positive. Sine will become positive. So if we try to represent this the surface energy into polar coordinates, for example, like so if we try to represent student, we try to represent this gamma this surface energy versus theta. If we represent this in polar coordinates, if we represent terms into polar coordinates, then if we only represent like theta will be from 0 to 90, if gamma is our r coordinate and theta is our theta coordinate in polar coordinates, then this graph will look like this. And if we do it for theta 90 to 180, it will look like this, and 180 to 270, it will look like this, and 270 to 360, it will look like this. So finally we have our gamma, the surface free energy, which is changing with respect to theta. Now from this we define the equilibrium state. Not the equilibrium state, the equilibrium shape of a particle. So this is how do you define the equilibrium diagram, or the equilibrium, not equilibrium diagram, the equilibrium shape of the particle. If I represent it like this, suppose if I draw a tangent, if I draw the surface free energy from here to here, and there I draw a tangent, and if I do for all points where the surface energy or where the gamma is minimum, there the tangent will cut most of the tangents. So if I draw the tangents at those points, it will become a cube. So from the polar coordinates, from the polar diagram, we define our equilibrium shape of the particle. So the same, this is called the Wolf diagram. So from drawing the surface free energy into the polar coordinates with respect to the theta, and after drawing the tangents and where we find the surface free energy is minimum, and if we draw a particular surface to that, we have the formation of a surface, and we have a formation of the equilibrium shape of the particle, equilibrium shape of the body. And for 111 we have very complex. If we have a cross section, then for 111 we have like a hexagon. So the wolf should look like this. That should look like this. And here are the tangents. So the equilibrium shape will be the hexagon, and if we draw the tangents, so I will stick here. Give me a second. This is like this. Then we have a hexagon. One, two, three, four, five, six sides. So should be this. That is how we define the equilibrium shape of any nanoparticle or any nanoparticle or the small particles. Let's see. Yeah. So far we know how this derivation has arisen, and also we know and sorry, I didn't mention this term, and we call it as a cusp. So where the energy with respect to theta or the surface energy will become minimum. See, and this is our time. And this point, this point is called as a cusp, where the free energy is not the free energy, the surface energy is minimum, and we got our relation, which is surface energy is equal to cos theta plus sine theta, sine modulus of theta, to maintain the positive sign in the sine theta multiplied by the surface free energy. So not the surface free energy, it is a bond energy divided by 2 times the lattice parameter square. From there we define it for the polar coordinates. Yeah. Now let's come to the thermodynamics part. So far we know many people have studied in thermodynamics course, any thermodynamics course, the metallurgical or mechanical thermodynamics, where there is a famous relation of Gibbs free energy, which is given as G equals to enthalpy minus temperature times the entropy. So there is one infamous and fundamental equation in thermodynamics, which is the Gibbs equation. Now, what I'm going to do is I'm going to differentiate it. So if I do the differentiation, it will turn out to be dg is equal to dh minus s times dt minus t times ds. Sorry. Minus sdt minus tds. Give me a minute. Yeah, it is recording. So we have dh is equal to minus sdt minus tds, and we know enthalpy equals to the internal energy plus P beta. So if I can differentiate dH, it will become dH equals to differential of internal energy plus PdV plus VdP. And if I substitute in this equation number 1, that will turn out to be, dg equals to what is dh? dh is de plus pdv plus vdp minus sdt minus tds. And the internal energy term plus pdv, which is equal to which will be equals to the first law of thermodynamics. The first law of thermodynamics has a very basic equation which states the energy of the system equals to internal energy plus PdV term. There is any other work. There is a PdV. There is a work. Or sorry, it shouldn't be like PdV. It should be the work term. And we know in terms of pressure and volume, we define it as a PdV. So work done is PdV against our system is turning to against the environment is doing work against the system. So this dE plus PdV will be equals to dQ plus VdP minus SdT minus TdS. Let's move to the next slide. I'll just take a second. I will add more slides. this equation again. dg equals to dg equals to dq. We shouldn't be writing as a exact differential, because dq is not a straight function, it is a path function. For path function we write it as a delta, but for simplicity I'm just writing it as a dq. Okay, let's just change it. Let's just change it. Yeah, I will write as delta q. We will left behind delta q plus vdp minus sdt minus tds. Yeah. So from second law of thermodynamics, where it tells about what is the extent of the work or the heat energy that is supplied is converted into something that from that we have a very famous relation, which is given as del q equals to delta S divided by the absolute temperature T. So del S or ds will be equals to d. Sorry, I write it the other way around. So, del S equals to del Q divided by T. So this is the relation. So entropy is the first entropy observation was experimented in terms of energy, the heat energy, and in terms of temperature. So delta S equal to dq by T, or we can even represent like this. So ds is equal to dq by T, then dq is equal to tds. So dg equals to del q, then the del q will be tds plus vdp minus svt minus tds. Minus tds plus tds gets cancelled, so we have dg is equals to vdp minus SDT. So good. So this is a free energy equals to VDP minus SDT. Then this, yeah. So this is our final equation for any system. If there is a change in free energy of a system alpha, then this is the free energy change of that system alpha. And we can write this dg alpha equals to, if we are assuming it, if we are taking it for a system, dg alpha is equal to v times dp alpha, or v alpha shouldn't be dp alpha, it's v alpha minus dp s alpha into dt. If we have another system like dg beta, it can be written as v beta dp minus s beta dt. So far so good. So now where we are going from here? Where we are going from here? So I missed a slide. So dg beta is equal to v beta times dp minus s beta times dt. So now the next question is how the lattice parameter is going to affect the melting temperature, or the melting temperature of metallic nanoparticles. So if we have a gold bulk material, for example, if I have 1 kg of a gold block, it has a certain fixed melting temperature. Now what happens if we have a gold nanoparticle? So how is there is a change in melting temperature? Like it remains constant or it increases or decreases. So what is going to happen? So we are going to define the relation between the particle size of the nanoparticle, the particle size of the nanoparticle versus the temperature or the melting temperature of the gold nanoparticle, gold or any other metallic or alloy nanoparticle. So let's take, I have a solid and I have a liquid, and I define it as a alpha and I define it as a beta. So here is the melting transformation. We have a solid and we have a liquid. This is melting transformation. So we have a solid, we are representing it as an alpha, and liquid we are representing it as a beta. So what's going to happen? Let's continue. Let's define. Let's write the change in free energy of alpha equals to dg alpha is equal to v alpha dp minus s alpha d alpha dt, right? Should be it. What about beta? That is dg beta equals to v beta dp minus s beta dt. So at equilibrium, what happens? At equilibrium we have dg alpha equals to dg beta. So if I take it as like this, if we take dg alpha is equal to dg beta, then alpha dp minus s alpha dt equals to v beta dp minus s beta dt. So v alpha minus v beta dp equals to beta minus s alpha dt. So this will turn out to be dp divided by dt equals to minus delta s divided by delta v, and this term is a famous one. This equation is called as Glass's Kaplan equation, which tells about how the pressure is changing with respect to how the pressure changes with respect to the temperature when two systems are in equilibrium. So let's go. We have an equation dp divided by dt equals to del s divided by del v. This will turn out to be dp by dt equal to minus s del s into del v, and at equilibrium temperature the change delta g minus del g minus dg alpha minus dg beta is equal to 0. So delta h must be equals to T delta s. Then delta s equals to delta h divided by T. And if I substitute there, that will be equals to delta h by T delta v. And if you are talking about the condensed phase, the equilibrium state between the condensed phase and the vapor phase. So for example, if we have a liquid and if we have a vapor, or we have a solid and we have a vapor, so represent it as a gas. Should be better. So we have a gas liquid interface, or we have a gas solid interface, where the volume of a liquids and solids is very much greater when compared to volume of gases. So let's just take it down here. This will be delta V is approximately equals to volume of gas. Why? Because volume of gas is much greater when compared to volume of solid of equal moles. If we take we are talking about equal moles, then this dP by dt will turn out to be delta H by T, and if we take that gas as an ideal gas, then Vg will be RT by P. So here we have R, already we have T, so it will become T square times P, and if we write it like this, we have dP by P equals to minus del H by RT square dt, and this will be P or delta P. If I do the integrate, sorry, mistake. This is not delta P, it will be ln P, because integral of dP by P will be a ln P. So we have ln or natural logarithm P by P naught equals to, if we do the integration, then that will turn out to be x power n, integral of x power n will be x power n plus 1 by n plus 1, so as we go out, then we have delta H term divided by RT plus ln A, so ln P by P naught, let's go again, so that delta H by RT, so it will be exponential delta H divided by RT into constant A. So this is how the equation turn out to be if you are talking about the equilibrium between a condensed phase and vapor or gas phase. For just like I have mentioned before, if you have a solid liquid interface, or sorry, not solid liquid interface, if we have a liquid gas interface or solid gas interface, so this is how it turns out to be. So let's move to this. dP by dt equals to minus, yeah. So from here we went all the way there. I will explain it again. You have free energy equals to the famous Gibbs free energy equation, which is equals to free energy equals to enthalpy minus temperature times the entropy, and the dg will be equals to dH minus sdt minus TdS. And if I differentiate, then we have dg is equal to dH minus sdt minus TdS. Then if I then after that we have enthalpy term relation where enthalpy equals to the internal energy times pressure into volume. So if I differentiate the enthalpy term, where dH equals to dE plus PdV plus VdP, and if I substitute dH in that term, it will become dG is equal to dE plus PdV plus VdP minus sdt minus TdS, and we know dE plus PdV equals to dQ, so dG is equal to dQ plus VdP minus sdt minus TdS. Let's write it like this. Yeah. Then we have dg equals to del q plus vdp minus sdt minus TdS. Again, from second law of thermodynamics, we have ds is equal to del q by t, and yeah, so when we substitute del q there, it will become TDS plus VDP minus SDT minus TDS. Now TDS gets cancelled. We have finally arrived at DG is equal to VDP minus SDT. And for suppose if we are talking about two phases that are in equilibrium, like alpha and beta, and we can write this differential term for that phases. For example, there is a small change in free energy in dg alpha that can be written as dg alpha is equal to V alpha dp minus S alpha dt. And if there is a small change, free energy change in beta, then that will be written as dg beta is equal to Vb dp minus SB dt. So yeah, and finally we arrived at this dp by dt. And if these two phases are in equilibrium, then we have a term called dg. And then if these two phases are in equilibrium, then we wrote it as dg alpha is equal to dg beta, and we know dg alpha is equal to V alpha dp minus S alpha dt, and dg beta is equal to Vb dp minus SB dt. And if we do some mathematical approximation and some mathematical jugglery, then finally arrived with this equation, which is called as a Clapeyron equation. And and for at equilibrium, for d delta g, which is dg beta minus dg alpha, or delta g beta minus delta g alpha, because at equilibrium both free energies of beta and alpha are same. They will be same, so delta g is equals to 0. So delta h equals to T times delta s. So delta s equals to so when enthalpy equals to T times delta s, and from there we define this change in entropy term or delta s term. So if we substitute this delta s term into the Clapeyron equation, which is equation number 2, we finally arrive to this equation. And if we again solve it by integrating and then writing the constants, we arrive to this equation. Finally, the final equation is the equation 3, which is equals to ln P by P naught is equal to E times delta H by RT into A. So I shouldn't write here ln, because I have taken exponential, so this ln will come out. So which is P. If I take atmospheric pressure as 1 atmosphere, then P naught will become 1. So P equals to A times E power delta H by RT. So this is how the pressure changes. Now, the next question is how the particle size affects the melting temperature. Just give me a second. I will add some more slides. Particle size are inversely proportional to melting temperature. is how it going to happen. So we have a relation like T is equals to T naught minus gamma energy divided by the particle size. I'll write it as some constants. Some constant C1 multiplied by gamma, the surface energy, which depends upon the size of the particle, divided by R. So this is the melting temperature relation. Now, if the size of the particle increases, so for example, if the size of the particle is too large, like we have a very large particle size, then this will term go on decreasing, this total term will decrease, and finally the Tm will be equals to T naught, or the equilibrium melting temperature. What happens if the size starts to decreasing? Then the problem arises. So T naught minus C1, so R divided by R. So the T naught, if the particle size starts to decrease, then this term will increase. So Tm will be less than T naught, or the melting temperature. Melting temperature will be less than the T. Here the T naught is, I should write it equilibrium or like bulk melting temperature. So the T naught will be equals to equilibrium or bulk melting temperature. And then so yeah, we have a relation. If we try to draw the graph, then we have a temperature and particle size. So reach out to T naught. So this is how it happens. That is how the size of the particle will depend upon the melting temperature. So if we started to decrease the size of the particle, the melting temperature will also decrease. Melting temperature. So that is how it's going to change. Give me a minute. Let me see. So how we are going to melting point? So the melting point of nanoparticles can be significantly lower than the melting point of bulk particle. This is because the melting temperature of material scales with its dimensions as it decreases towards the atomic scale. Now it also depends upon the crystal shape, the type of crystal it is made. We have a very close packed structure, then it will require more amount of heat to melt that particle, and it also depends upon the radius of curvature. Also then affects this melting point. So if I draw the relation, the graph should look like this, and the size should decrease. If the size should have decreased, so this is how it should go, and that is its the trend. Now it also depends upon whether it is supported or it is confined to a certain structure, and that is also takes a bit on to the melting temperature. And now let's move on to the where it is it? Yeah, it should be here. In thermodynamics part, we had Gibbs free energy derivation, where we have a Gibbs free energy equation, and from the Gibbs free energy equation we define the partial change in how the partial change in Gibbs free energy, and from there we define the classic Kaplan equation, how the pressure term it's going to change with temperature. It's there. And the next term is, let's write for, it should be Tm equals to T0 minus C1 times free energy which depends on R divided by the size of the particle. If we move on to the next term, next topic. From here we can define the equation del P tau should be equals to should be written as the del P R del T to T1 times T0. So then we have del P, which is equals to, let's move to the next slide. We know that del P will be equals to 2 gamma divided by R, the excess free energy, or the excess pressure, sorry, not excess free energy, it is excess pressure, 2 times the free energy divided by R. Comes divided by R, and we have P. We can write it like this, which is, if our surface is medium 1 and we have medium 2, we have P1, here we have P2, or we can write it as P alpha. We can write it as P beta, P alpha equals to P beta plus excess free energy term, which will be 2 gamma divided by R. So that P term, which is, if we take out the P will be P alpha minus P beta, rewrite it those terms where we wrote it as, let's move on to the initial term. It's quite confusing to write like that. So dg alpha equals to dg beta, then we have v alpha dp minus s alpha dt equals to v beta dp minus s beta dt. So if you subtract v alpha minus v beta dp equals to s beta or s alpha minus s beta dt. Should be s alpha plus s beta. Yeah, this is how it should be. There should be minus here. Forgot to keep minus. There won't be any minus. Sorry, there won't be any minus here. Yes. Here we are. So dp will be del p, that is equals to 2 gamma by r is equals to del s by del v times dt, and we know del s is 2 gamma by r, del s is del h by t, dt. Should be like this term, yeah. Then this will be turned out to be just a second. I will write it. I should write it here. I will just write it as dp. Then here we have dp. Here we have dp. Now if we try to integrate it on both sides, this will turn out to be delta p equals to del h divided by del v multiplied by log, sorry, natural logarithm d2 by d. So del p is 2 gamma here T1 is equal to equilibrium melting temperature or we can even write it as a bulk melting temperature. Good. Then let me add few more slides. We have bulk melting temperature, yeah, then that will turn out to be